Welcome to Section 7-1, Exponential Growth. Chapter 7 is all about these things called exponential functions, and I'll tell you, of all the high school math that I ever learned, the stuff in this chapter is probably the stuff that I use the most in my actual life. And I'm not just saying that because I'm a math teacher. I'm saying that because exponential functions are used to model money. Whether you're investing money or taking out a loan or you have something that is losing value or gaining value, exponential models mimic those situations. And I promise you, if you understand the concepts from this chapter really, really well, you will handle your money better than people who don't. And we'll do a lot of money examples in this chapter as well. So a lot of times when exponential growth is introduced, you'll see this trick question, and they'll give you two deals, and the question is which one is better? Which one for you is financially better? Option one is I give you $1 million right now, ton of money. Option two is I give you a penny today, and tomorrow I'll double it and give you 2 pennies. And then I'll give you 4 and 8 and 16, and I'll double it every day, how much I give you for 30 days. And it's a throw-off because you think, boy, $1 million is a lot, a penny is not so much. And when we can see, even when we run the numbers, that bears out. If we put the day on the left side and the money on the right, let's call the first day, day 0. I haven't doubled it yet. So on the first day, I give you a penny. Then after that, on day 1, the first day I double it, I'd give you 2. And then on the second day of doubling, I'd give you 4. And on the third day, I'd give you 8. And gosh, if we add all this up, after 3 days of doubling, you only have 15 cents. So boy, the $1 million is looking pretty good. But lo and behold, and I won't make you fill the chart out, but if I get all the way to day 30, here's how many pennies I give you on day 30. It's 107,3741,824. And that translates to approximately $10 million worth of pennies. And so if I give you on day 30, if I end up giving you $10 million worth of pennies, that means on day 29 I gave you $5 million. And so we're kicking the $1 million butt all day. The idea is when we think about exponential growth, it grows fast. And so that ends up being the better deal. Now what I've created here is an input-output chart, right? I've got input, output, and usually input-outputs, those are defined by a function and equation. And it turns out all exponential growth can be modeled with the following. Y equals A times 1 plus the letter R raised to the T. Now, of course, A, R, and T, the letters in there mean something. Okay, the letter A is your initial amount. How much do I start with? In this case, 1 penny. T, not surprisingly, is time. How many days, how many years? The units can vary, but how long are we talking about? And R stands for the rate of growth. And that is always expressed as a percent in decimal form. And what I mean by that is 50% would be 0.5, 75% would be 0.75. So for our problem right here, let's see if we can come up with the equation that defines this penny problem. We'd start with Y equals, and we'd give the initial amount. The initial amount is right here. It is 1 penny. And then we've got 1 plus. It's always 1 plus. And then we got to think about the growth rate. How much am I growing by? Well, I fully double my money. That is 100% growth, or as a decimal, the number 1. If 50% is 0.5, 100% is 1. And then time remains the input. I input time, I output my amount. Now, since 1 plus 1 is 2, this is really Y equals 2 to the T. And keep in mind that multiplying that 2 by 1 doesn't do anything. So, 1 times anything is itself. So Y equals 2 to the T. And we can see that this works because let's say I was looking for day 4. I could use my model and say 2 to the 4th, which is 16. And that seems right because 4 times 2 is 8, times 2 is 16. The model seems to work. Now, once we have our model, we can do whatever we want with it. But one thing I'd like to do, because we've looked at the numerical representation of exponential growth. Here's the algebraic one with the equation. Let's see what this looks like visually, the graphical representation. So I'm going to plot some points here. And so we know that on day 0, initially we start with the 1 penny. And then on day 1, I double it and I give you 2. So you have 3 pennies now. On day 2, I give you 4. And on day 3, I give you 8. And I'm not going to go any farther than that because I'm going to run out of graph. But if we play connect the dots, we get a shape that looks something like this. Now, kind of looks like half of a parabola. Believe it or not, it's not a parabola. And you'll see that in a second. Because you know what I'm going to do? I'm going to continue my input-output chart. Except I'm going to try some negatives. I'm going to try -1, -2, -3, and -4. I'm going to see what happens in the world over here on this side of the y-axis. Now, understand that, of course, this doesn't make a lot of sense when we're talking about days, right? Because I can't really have negative days in this situation, but bear with me. Let's see what happens. So, according to my model, it's 2 to the time, and the time I'm giving is -1. And we know from exponent rules that's the same as 1 over 2. So input a -1, output a half. 2 to the -2 is 1 over 4. Right, so 1 over 4, okay, I'm getting kind of close here. This is a little bit hard to draw this dot, 1/2 and 1/4. 2 to the -3, that's 1 over 8. So I'm a little closer here to the x-axis, and this is about as far as I think I'm going to be able to plot. 2 to the -4 is 1 over 16, so I'm pretty much right on the axis. And what I notice is that it seems like I'm hitting some sort of a barrier here, like I'm not ever going to be able to cross down into the negative numbers, almost like the graph is going to do something like this. And in fact, that's exactly what it does, and you can see why I said this doesn't look like a parabola. So what happens is that the graph cannot cross into the world of negatives down here because there is no way to input. Right, our function is y equals 2 to the t. There is no way to get a negative output because when I input negative numbers, I don't get negative outputs, I get fractions, and that's because of the rules of negative exponents. So what ends up happening is as I input bigger negatives, I get fractions that have bigger denominators. I'm getting closer to 0, but I can never touch it and I can never cross it. And there's a math term for this. It's called, this is a big 25-cent word, it's called an asymptote. Asymptote. And big word, simple concept. It is a line the graph approaches. It's a line the graph approaches, but does not cross. So it gets closer and closer to that, in this case, x-axis. It's the x-axis for y equals 2 to the t. Now, not every exponential growth function will have the same asymptote, but they will all have an asymptote, an imaginary line they can't cross because of what we know about negative exponents. Another way to talk about this is in terms of a couple of concepts known as domain and range. And I like to bring these up because I think it's good. These ideas come up a lot in math, and it's good to keep in your head what these are. Remember that the domain, it's the inputs, it's the x values. And the range is what are the y values, what are the outputs. And for the x values, there's really no limit to what I can do for x values. You saw I input positive numbers, I input negative numbers, I could input 1,000,000, I could input 0. I can input for x, and by input I mean these guys right up here in the chart. I can input any number I want. So all real numbers are fair game. The output, though, is restricted. So I can get, as you see from my output list, all my outputs have to be positive. So the y value, the output value, the amount of money value, whatever you want to call it, must be greater than 0. And so there's a restriction on the range. That's another way to talk about the asymptote. Okay, so let's look at a real problem here. So this is just one I pulled out of your book, and it says from 1998 through 2003, the number of hits per month on a website can be modeled by this guy. So in other words, I am going to input the time, okay, how many years since 1998. So if I input a 0, I'm talking about 1998. A 1 is 1999, and so on and so forth. And it's going to output how many people visited that website per month. And so the first question we ask about this, really just as an understanding check, identify the initial amount, the growth factor, and the percent increase. Well, growth factor we haven't talked about yet, so let's talk initial amount. Remember, the model for all exponential growth is y equals a. 1 plus r to the t. And a, the thing right out in front, that's the initial amount. That corresponds to 2,500 hits. That's our initial amount right there, 2,500 hits. So we just pull that right out of the equation. The percent increase is a little bit trickier because I know that the percent increase comes from right here. It is 1 plus r, but I don't have 1 plus r. I have 1.5 in there. Well, if I have 1.5, the only way I could get that is 1 plus 0.5. So that right there, 0.5, also known as 50%, that's my percent increase. I am increasing 50% per year. Okay, and then finally, the growth factor. This one is the one that's pretty well already given to us, because what the growth factor is it is after you take the 1 and the plus 0.5 and you put them together and you get the 1.5, basically what was given already in the problem, that's what's known as the growth factor. Okay, it's just the terminology for it. So the percent increase is 50%, and when we combine that with the plus 1 and get 1.5, that's our growth factor. So there's the three pieces of information here, here, and here. So then it says, all right, let's go ahead and graph the function and use it to estimate the number of hits per month for 1992. And by the way, since that should be 2002. Now, when we go to do this, when we go to graph this, one thing we have to be aware of is that the graph here, it says 1, 2, 3, 4, 5. We got to adjust our units. So let's call for the years, let's call this guy, the first year is 98. This guy will be 99, 2000, 2001, 2002, 2003. Okay, those are going to be our numbers. And let's make this nice. We're talking about thousands of hits. So let's call the 1 actually 1,000, and the 2 will be 2,000, and so on, all the way up to 8,000 here. That'll be should be a good scaling for our graph. Now, what I did is I just inputted this function, this model, into the calculator, and the y equals 2,500 1.5 to the t, and I'm gonna pull some points off my table. So I know at 0 I'm at 2,500. I'm looking at my calculator. 1, I'm at 3,750, so almost 4,000. At 2, I'm at 5,600, so 2 would be the year 2000, 5,600. At 3, I'm at 85, so in 01, I'm at 85. I'm all the way up to here. And I can see the exponential growth taking place. And then I'm going to sketch in what I think is a good graph. Now, I'm going to then say, okay, I'm interested in 2002. So here's 2002, and I'm going to follow it up. And I'm going to see, now I'm kind of off my graph here, but this would have been 9,000. So right about here is about 10,000. And I'm a little past that, so I'm going to, and this is an estimate now, here's my intersection in 02, I'm going to guess about 10,500 hits per month. And again, this is just an estimate. If I really wanted to know, I could plug 2, 3, I could plug 4 for 4 years from 1998. I could plug that into my model and get the for real number, but I'm just using the graph to give a rough estimate. And by the way, what I really might use this graph for is if this was a current model, I might use it to predict the future. You know, if trends continue, if I keep growing exponentially, what am I going to do in the year 2015 or 2020, and that might inform some business decisions as to what I might upgrade or and so on. Anyway, I digress. But we'll be doing some more applications like this in class. So please come ready with your questions, and thank you very much for watching this.